Hi, so in this video we're going to look at some impulse graphs. So let's go ahead and get started. For these impulse graphs, it's going to be a force versus time graph. So force is going to be on our y-axis because this is our dependent variable. This is something that we are measuring. Time is going to be on our x-axis because it's something that we're changing. We can allow so much time to pass by. These are called impulse graphs because these graphs tell us the impulse that's acting on the object. So if we find the area under the curve or under the line, so between the line, so this line here, and our x-axis, we could find the area of this triangle and we would have some sort of positive value, meaning a positive impulse. For the next section of the graph, where we have it in the negative portion of the graph, you could treat this as a triangle and a square, and whenever you add the areas together, you would have a negative value. So this would give us a negative impulse. And it would be negative because, of course, all these values down here would represent a negative force. Maybe this is -5, -10, -15. So for some graphs, if it's a constant force, such as this one, you can see that it's a very simple shape. This is just a rectangle. For this graph, you can see that 2 seconds go by and then suddenly a force is applied. And a force of 12 newtons is applied because that's how high our graph reaches. And this 12 Newton force is applied from 2 seconds to 6 seconds. So really, it lasts for 4 seconds. So if we wanted to find the impulse that's acting on this object, we could find the area that's under this rectangle. So we would only find the area for this rectangle. We know that it has a base of 4 seconds and a height of 12 newtons. So our area for a rectangle would be base times height. So we would have 4 seconds times 12 newtons. So of course our area would be 48 newtons times seconds. So this would be the impulse on the object for this graph. Sometimes our graphs may not be as simple as just one rectangle. Maybe you might have a triangle. Again, for a triangle, your area would be 1/2 times the base times the height. For a rectangle, your area would be the width times the height. And for a trapezoid, your area would be 1/2 times a plus b, so these are the two sides that are parallel, times the height. So for this graph, it's considered to be a non-constant force. Because if you look on our graph, for the first 2 seconds, we are increasing in force. At first, no force is applied, then we're applying 10 newtons, 20 newtons, 30 newtons. We are increasing in force. Then from 2 seconds to 8 seconds, we have a constant force of 30 newtons being applied. Then from 8 seconds to 9 seconds, we are decreasing in force. We are dropping down from 30 newtons to 20 to 10 and back to 0. So if we wanted to find the impulses acting on this object for the 9 seconds that a force is being applied, we can find the area of this trapezoid. So, for example, this trapezoid, the two parallel sides, it's important to identify those parallel sides first because those are going to be your A and B, the two sides that you add. So one side would be this one. The other side would be this one. These are the only two parallel lines. It cannot be the two lines that are slanted because those are not parallel. They're slanted towards each other. Eventually they would intersect, so they're not parallel. So if we consider this bottom line to be A goes from 0 to 9 seconds. So A is 9. B is from this 2 second to 8 second mark. So 8 minus 2, this is 6 seconds. And then we have our height. And our height is the tallest line, our greatest amount of force, the maximum amount of force, the highest horizontal line. So this, of course, would be the 30 newtons of force. So our height is 30 newtons. So using our equation for area, 1/2 times A plus B times height, we can plug in 1/2 times A was 9 plus B was 6 times a height of 30 newtons. So when we plug this into our calculator, we would have 1/2 times 15 times 30. And this is going to give us 225 newtons times seconds. All right, so for this next graph, we're first being tasked to find the impulse. And again, the impulse, we are finding the area of this rectangle because this line here is our curve and we're finding the area under the curve, meaning this line between 0. So we know the area of a rectangle is base times height. Our base is the time, so the 0.8 seconds. And our height is 4 newtons. So when we calculate the area under the rectangle by multiplying, we get that the area of the rectangle is 3.2 newtons times seconds. So that's our joules. So we now know the amount of, impulse, not joules. We now know the amount of impulse that's acting on the object. And next we can find the final velocity of the object. So we know the impulse, we know that the mass is 2 kilograms, and we need to know the change in velocity. So the equation we're going to use is impulse equals mass times the change in velocity, which we know is really final minus initial velocity. And remember, if a problem doesn't say otherwise, we assume that the initial velocity is 0. So we're really using the equation impulse equals mass times our final velocity. So our impulse was 3.2 newtons times seconds equals a mass of 2 kilograms times our final velocity. Well, we need to divide by the 2 kilograms on both sides. And when we solve 3.2 divided by 2, we're going to get a final velocity of 1.6 meters per second. So that's the final velocity for this graph. I'll show you one more graph before we end the video. So for this graph, of course, our curved line is slanted. It has a positive slope. So to find the impulse acting on the object, we need to find the area under the curve. So between 0 and the blue line. So this is a triangle. So we know our impulse is going to be the area for the triangle, which is 1/2 times our base. And our base, we again go from 0 to 0.8. So 0.8 seconds. Times our height, we again reach the 4 Newton mark. So our impulse, when we plug this into our calculator, we have 1/2 times 0.8 times 4, and that's going to give us an impulse of 1.6 newtons times seconds. And then again, we're being asked to find the final velocity of the object with a mass of 4 kilograms after 8 seconds. So we have the impulse, we know the mass, and again, we're looking for the final velocity. And just like before, it doesn't tell us an initial velocity, we assume it's 0. So we're using the same equation. Impulse is equal to mass times the final velocity. So impulse is our 1.6 newtons times seconds, and it's equal to our mass of 4 kilograms times our final velocity. So of course we need to divide by 4 kilograms on both sides. And once we have 1.6 divided by 4 kilograms, that is going to give us 0.4 meters per second for our velocity. So a very slow velocity.